Hi, I'm Gary, and I want to show you how I use Cloudy. Okay, we've been talking about the cooling function and thinking about the case of the cooling function for solar abundances. We're going to take the cooling function one more step and think about the cooling for the interstellar medium. So we're going to add two commands to our existing script. This is what the script looks like to compute the cooling for the interstellar medium. So the red box shows the new commands. One, we're going to deplete the heavy elements according to the prescription in this Jenkins 2009 paper. So the second thing, that's going to remove elements from the gas phase due to condensation on the grains. And secondly, we're going to add the grains. So the grains ISM is going to use an astronomical silicate and graphitic component with ISM size distributions. So with that, we can compute the cooling. The effects that cool grains have, a dusty environment have on the cooling function, these four. First, there's going to be missing cooling from the gas phase because atoms are depleted onto the solid. So that means there's less oxygen to cool the nebula. So for a given heating rate, the gas has to be a little bit hotter. Next is what's called collisional energy exchange. Electrons and ions collide with the grains and they exchange energy in the collision. They're trying to come to the same temperature. The gas and the dust are not at the same temperature. In the H plus layer, the gas is much hotter than the grains. In the PDR, the grains can often be hotter than the gas. When they collide with each other, they actually come towards the same temperature. So in the H plus layer, the hot electrons are cooled by collisions with the grains, and it has an extra cooling. In the PDR, the grains are hotter, so that the grains tend to increase the temperature in the PDR. There's another heating process that's very similar to hydrogen photoionization. The material that makes up the grains that typically has a work function of about 10 eV. There's radiation between 10 eV and the Lyman limit, 13.6. So this 13, 12, or 11 eV photons can cause grain ejection from the grain surface. So the grain comes off with kinetic energy that's shared with the thermal electrons, and that then also acts to heat the gas, very similar to hydrogen photoionization. And lastly, we're going to find a very, very rich chemistry in this case. The grains help H2 form, as if by far the most efficient grain formation process is catalysis of grain surfaces. And once the H2 starts to form, all the other molecules form by direct or indirect reactions with the H2. So it's going to be many more molecules. This was the cooling function for pure solar abundances. I ran that first script and plotted it up, but we find the cooling function is very similar and very, very different. At low temperatures, the cooling can be different by order of magnitude. These ticks are one order of magnitude. So here, about 500 Kelvin, the cooling is about an order of magnitude higher. The details here on this inflection are quite different. This peak in the cooling function around 10,000, 10 to the 5, 10 to the 6 Kelvin is pretty similar. Remember, these are one Dix steps, so this, by saying pretty similar, maybe 50% different. And finally, at very, very high temperature, you find that the grains act as a very, very powerful coolant. So the differences are caused by these. At very low temperatures, the dusty case has a very rich chemistry due to efficient molecular formation, leading with H2 formation in our grains. There's enhanced low temperature cooling due to the presence of molecules with rotational molecular transitions at high. So this is something that atomic gas can't do. Uh, The At high temperatures, gas collisions with the cool grains cools the gas. We don't follow the time evolution of grains, but at high temperatures in that cooling function, the grains were cool enough to survive. The process of spallation will eventually destroy the grain. So that's when high energy particles collide with the surface and chip pieces off. We don't follow that. But let's finish by looking at some sample spectra. To compare these with the same temperature spectra we did in the solar case. So at low temperatures, what you have here is a very bright molecular cloud. The just too many molecular lines to see. Until the fourth Kelvin, it's high enough temperature to dissociate many molecules, but you can see they're very prominent rotation brand heads in the submillimeter, and the Webb region of the spectrum has very, very strong lines. So it'd be very interesting to see such gas. At 10 to the 6th Kelvin, the spectrum doesn't look a lot different than it did with the dust-free case. There's strong emission, lots of lines, and they're all in this unobservable part of the spectrum where the transmission of the ISM blocks our view. Finally, at 100 million degrees, you expect to see very strong X-ray emission, hard X-ray emission due to iron, that the iron K alpha, the 2 electron K alpha triplet. Uh, the iron lines are very, very weak due to iron depletion. There are still some lines, but this hot spectrum is quite a bit different. So with that, we've seen the cooling function depends a lot on details. It depends on solar abundances, and we're going to talk next time about how the cooling function interacts with photoionization heating to establish the temperature of an ionized nebula. See you then.